Hey guys, happy Friday. We have some notes for class today, but instead of doing them in front of you guys today in class, we just did this quick video, which looks like there's a lag. Now I'm good. All right, so for this video, it's pretty much covering the sun, what we covered the last 2 days. So notes are pretty straightforward. It's just one page of notes, getting this ready for our test next Tuesday. So what I want you to do in your table of contents, I don't have that here. In your table of contents, I want you to write the sun and whatever page you might be on. Ooh, that came out really big. Let's see if we could zoom in a little bit better for you guys. There we go. All right. So what we're going to do here is take these notes. They're done for you already. So hopefully you're listening to me. You're not just copying these notes. So hopefully you listen so you get some more information. So let me get my pointer here. There's my little pointer. All right. So the sun. And what I want you to do is draw this picture of the sun. You could use yellow highlighter if you have it. And we're just going to label a couple pieces of the sun, all right, that we want to know. We're not going to label everything on the sun because we don't have to know that for our class. So the first part, what I want you to label is called the photosphere. It's the surface. That's what you see. So if you draw your little arrow right here to the yellow part right there, that is what's called the photosphere. That's the surface, and that's what we see with our naked eye. The next part I want you to label is the core of the sun, so the middle of the sun. This is where all the nuclear fusion occurs. This is where the sun gets its energy from nuclear fusion in the core. So that's the inner part of the sun. And the next part I want you to label is the corona, and that's this red part going around the sun right here. Okay, my page is moving. I apologize. So remember, the corona means the crown. That's the weak atmosphere surrounding the sun. It's only visible in an eclipse. So some of those pictures we showed you where the eclipse was going across the sun, you could see the corona coming around it. Also, the corona, if you didn't know this, we don't have to know, the corona is actually hotter than the surface of the sun. We don't know why yet, but hopefully with science and through some satellites NASA has in space now, we'll be able to figure that out. So that is the photosphere we talked about, the core, and the corona. All right, going down a little bit. I don't think we talked about this term yesterday, but a lot of stuff that you guys saw yesterday fell into this category of coronal mass ejections. So what that means is the atmosphere, the crown, all right, gives off ejections means gives off large amounts of atmosphere. So this is where you saw stuff flying off of the sun yesterday, and there's different types too that were occurring that we showed you. So the first one we showed you was a solar flare. So solar flares are ejections of gas so strong it is not able to be pulled back in. So when you saw those ejections of gas leaving the sun and not being pulled back, that's what's called a solar flare. And today in class, we did a Kahoot, and you guys saw some pictures of solar flares. Our next coronal mass ejection category are what's called a solar prominence. So these are ejections of gas that loop back in by the sun's magnetism. So they're the arching ones. So they'll arch back. Oh, you can't even see me. Where's my finger? So they arch back to the sun. All right. So you saw a lot of these images yesterday. So they're brought back by the sun's magnetism. So they're not strong enough to actually leave the sun like a solar flare. Our third category of coronal mass ejections. Let me here. My computer is messing up on me here, guys. Hold on. There we go. Is called the solar wind. So what the solar wind is, it's a constant flow of gases from the sun that interacts with planets like Earth. All right. So that's why the Earth's magnetic field protects us from this solar wind. And it sends that solar wind to the poles, to the north and south poles. And what we see happening in there, and we showed you pictures of this yesterday, and you saw it today, you get what's called auroras. These are the interactions between the solar wind and the Earth's magnetic field, which create these brilliant lights at nighttime over the north and south pole. So pretty cool. Try to see those at least once in your life if you ever get a chance. They're really, really cool. And last but not least, on our notes. I said these notes were not long. Oh, I forgot to talk about this. The color tells you the chemical composition. So what we mean by color there is the color of the auroras. So remember when we lit stuff on fire in class and we were able to create different colors with different elements? Same thing with the auroras. So if it's a green, blue, red aurora, that tells us what chemical composition it's being mixed with in our atmosphere. So pretty cool. So the color of the auroras tell you the chemical composition. Okay, so that's the last thing with auroras. And the last thing for our notes are sunspots. So we showed you some images yesterday and today. Remember, these are the spots on the sun surface that are cooler than the sun, than the area surrounding it. All right, so if it looks darker, it's cooler than the area surrounding it. It's still hot, but not as hot as the area around it. And sunspots move, all right? They don't always stay in the same spot on the sun, and they go through cycles. So sometimes there's more sunspots than other times in the sun's lifespan. So they're constantly changing these spots. So these sunspots are cooler areas than the surrounding area around it. All right, that's the notes. I have a quick video that I added on here that I want you guys to watch. It's about space weather and how it affects Earth, and they'll probably tie in a lot of stuff that we covered in these notes. So I'm going to pull that up. Again, please stay on. Don't turn the video off, and we'll get started right here. I'll make it nice and big for you guys.
The sun is often referred to in astronomical texts as a garden variety star, which is okay because it is fairly common type, although I object to it sometimes because garden sort of implies uninteresting.
We can have energy from the sun that affects our communication systems. It can also affect satellites, space missions. It can cause problems with power grids and things like that.
This is Kitt Peak National Observatory and the National Solar Observatory. This is a pretty sunny site. We're in the southwest in the middle of a desert at a fairly high altitude, about 7,000 feet. So we're above much of the atmospheric haze that lies down in the lower desert. This is called the Solar Vacuum Telescope. It's a special telescope to observe only the sun, making a special use of mirrors to produce a stationary image inside an observing room. The actual observing apparatus then consists of a spectromagnetograph, which is a special instrument designed to look at the sun's magnetic field. The magnetic field is probably the fundamental physical mechanism which controls the outer solar atmosphere. It's because it varies and changes that particles become accelerated and that they're directed towards the Earth. The areas of strong field, probably here, here, here. This region in particular is an example of an active region. It's a region that is likely to erupt, where large volumes of the sun simply are ejected out into interplanetary space. And that is at the heart of space weather.
Space weather starts at the sun, and the sun's atmosphere explodes off of the sun, and it flows out into interplanetary space in all directions at about 1 million miles per hour. And then when that flowing solar wind impacts the Earth's magnetosphere, hits the Earth's magnetic field, some of the solar wind particles and some of that flowing energy get trapped. And when the energy energy is released. It causes enormous acceleration of particles that give us the radiation belts that impact astronauts and impact satellites. It also generates the aurora borealis that we see, and it drives large electrical currents in the high-latitude ionosphere that can impact power transmission on the ground, pipelines, communications, those sorts of things. And then on top of that, the sun occasionally blasts off these large coronal mass ejections, and when one of those impacts the magnetosphere, it's just like hitting an already stressed system with a very large wallop, and that causes some of the largest space weather activity that we see.
Good morning, Space Weather Operations. This is Ken.
The largest flare was an M2.
That's an incredibly impressive region.
All solar activity does not hit the Earth, CMEs, solar flares. It depends where they originated from on the sun and where we're located in space. Something that's located in the middle of the sun, from there, heading straight toward the Earth would be the most likely direct hit.
Right here, that's the one that has been giving us most of the activity.
The data that the Space Environment Center uses is a collection of ground-based and space-based instruments. Solar forecast, moderate to high. M-class flares are likely. Our forecasts, our information, our alerts and watches and warnings go out to a variety of customers. Power companies receive our information. Operations centers that are operating satellites, airlines use our information for radio blackouts. Geologists use our information for checking their instruments before they drill. Our forecasts on the short term are not bad at all. They're actually pretty accurate. Long term, even with the weather forecasts, it's difficult to say things, 3 to 7 days out.
I think the day will come when space weather reports become mainstream in our society and our news broadcasts and our newspapers, because we're certainly using space more and more, and I think we will continue to, and we're relying on it more and more for our economy and for our standard of living. And as we use space and rely on space, space weather information is likely to become more prevalent in our daily lives.
Space Weather Operations, this is Gail.
All right, so hopefully you enjoyed that video, got a little bit more about space weather. Have a great weekend. Hopefully you get these notes today, and we'll see you Monday. Review, test on Tuesday. Later.